As you can see here, we're going to discuss a library of functions, and really what this is about is a set of seven different functions that I want you to be able to anticipate what the graph will look like without getting out your graphing calculator. We need to be familiar with the shapes of some graphs. Otherwise, we're not getting anything done. And as you go further into your math career and getting into calculus, you're going to have a pretty good idea of what some graphs look like before you ever get started. You're going to have to recognize from the formulas. So here are the graphs, or here are the functions. F of x equal x squared. I want you to know what that looks like without getting out your calculator. F of x equal x cubed. I want you to know what that looks like without getting out your calculator. And we'll talk about these here in just a moment. But you can look at these in your book as well. Those are called power functions because they're x to a power. Okay, then I want you to know what the graph of f of x equal the square root of x looks like, and f of x equal the cube root of x. Now, these are called radical functions or root functions because they're a square root and a cube root. And of course there are other variations. There's fourth roots, and there's, back over with the power functions, there's f of x equal x to the fourth and so on, but that's not what I'm worried about at this moment. And then there's a couple of more. F of x is equal to the absolute value of x, and we probably already know what that looks like. And the sixth one, f of x is equal to, this is called the ratio function, 1 over x, and then the constant function. Okay, and a constant function is something that looks like f of x is equal to a constant, or just say c, some constant number, like f of x is equal to 5. That would be a constant function. Or it could be f of x is equal to -3, or f of x is equal to 1/2, or f of x is equal to 271. But what f of x is equal to is a constant. It doesn't involve any x's at all on the right side. Okay, well, I'm not going to bore you with this in each case, but let's look at f of x is equal to x squared. And so when we're thinking about graphing this, let's think about plotting points real quickly. Maybe you know what it looks like already, but I'm going to go through this. Then what we do is we choose some x values, and we calculate the y values, and in this case the y values are calculated with x squared, aren't they? So if we choose x to be -3, for instance, then our y value would be +9, wouldn't it? We choose x to be -2, then our y value, when we square -2, we get +4. We choose x to be -1, our y value will be equal to +1. If we choose x to be 0, then of course our y value is 0. Y would be 0 squared, which is 0. And then we could choose x to be 1, 2, and 3, and in that case we would get a y of 1, a y of 4, and a y of 9. I'm going to choose one more. I'm going to choose x to be 1/2, and so y will be 1/2 squared. Well, 1/2 times 1/2 is 1/4. Okay, so let's quickly sketch this. And I'm ready to plot some points. And one of the things that I noticed here is all my y values are either 0 or positive, and of course they're going to be because I'm squaring whatever choice of x I make. And I could have chosen x to be 791, but my y value would be that number squared, and obviously my graph would be way too big for me. So I've chosen some fairly small x values here. So when x is -3, let's make sure that we understand that each of these tick marks is 1 unit. So here's where x is -3 and y is 9. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is where y is 9, right up here. And so we have this point on the graph. Okay. And when x is -2, y is 4. 1, 2, 3, 4. This is where y is 4. So we have this point on the graph. And when x is -1, we have a y value of 1. So this point's on the graph. And then 0, 0 is here. 1, 1 is here. 2, 4 is here. And 3, 9 is way up here. I plotted one more point. I did one more point. X is equal to 1/2. That would be there, wouldn't it? And y is equal to 1/4. That would be roughly about like that. And I've done that point specifically to show that down here at the vertex, we're actually rounded and not pointed. That's what I wanted to point out to you here. And so we have a graph. Whoops, oh, I missed those points, didn't I? Now, in this case, the graph does go on. We just haven't plotted all the points, have we? And this is called a parabola. Okay? And so we should know what this graph looks like pretty quickly. And we ought to be able to get, with just a few reference points, those reference points that I've circled there really are the points that I'm dealing with right here, aren't they? And so with a few reference points, we can sketch that graph pretty quickly. Now, on the other hand, if we look at f of x is equal to x cubed, okay, well, if I were to start creating a solutions table here, I can get out of hand real quickly. And so here's what I'm going to do. I'm going to choose x's and get y's. And I'm going to choose x to be -2 because when I cube -2, I get a -8, don't I? -2 times -2 times -2. Remember, we're cubing our x. So if I chose x to be -3, my y would be -27, and it's huge, of course. Choose x to be -1, I cube -1, I get -1. -1 times -1 times -1 is -1. I choose x to be 0, I get 0. I choose x to be 1, I get +1. I choose x to be 2, I get +8. So when I'm drawing this graph, I may scale a little differently here, just because I don't have the space, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I don't have a space. So I'm scaling it a little differently. Okay, so on the x-axis, I'm going to let each one of these be 1 unit. And on the y-axis, I'm going to let each one of these be 2 units. So this is +8 here. And this is -8 here. Of course, this is -2, -4, -6, and so on. +2, 4, 6. But this is a 1 and a 2 and a 3. And this is a -1, a -2, and a -3. Now, when x is -2, I have a y of -8, which is down here. And when x is -1, I have a y of -1, which is actually about right there, as I've covered up my point. And when x is 0, y is 0. And when x is 1, y is 1. So that's about right here. And when x is 2, y is 8. So about right here. So when we draw this graph, it kind of looks like we took part of that parabola and turned it upside down. That's what it looks like. That's not really what happened. Well, that's not the best graph. I apologize for that. But we have that shape in general. So once again, if we understand what these 3 points in the basic shape of that graph, that is using these 3 reference points in the basic shape of that graph, we ought to be able to sketch it pretty quickly without a calculator again. Okay, keep saying that, don't I? Next page. So as we graph the square root function, we run into a different set of issues. And the issues that we run into here is the domain. Let's make this note. The domain is the set of x's such that x is greater than or equal to 0 here, because we can't have a negative value under the square root. So our x values, what's under the square root, has to either be 0 or positive. And so there's no sense choosing negative numbers for x, because that's not in the domain. But we can certainly choose a 0 for x, and y, of course, we calculate by finding the square root of 0, which is 0. And we could choose 1 for x, and if we did that, our y value would be the square root of 1, which is 1. And we could choose 2 for x, but then our y value would be the square root of 2. And unless we approximated that with our calculator, and right now I don't really care about that, but it's approximately 1.4. So we might choose next time an x value that we can calculate y pretty easily for, so we choose x to be 4, and our y is the square root of 4, which is 2. And then the next x value that's useful to us would be 9, because y would be the square root of 9, which is 3. So this graph looks different because it doesn't go in both directions forever. Let me set up, and notice this, the x values are getting big fairly quickly there because of what I had to choose. The y values aren't getting big very rapidly. Okay, I've set up now you see I kind of messed up my x-axis there. I apologize for that. Now, since we couldn't choose any x's that were negative, the very first x that was possible was x being 0, and when x is 0, y is 0, so that point is on the graph. But that's the furthest to the left point there is. And then when we choose x to be 1, we got y as 1, so that point is on the graph. When we chose x to be 2, we got y as the square root of 2, which, as I mentioned to you, is roughly 1.4. Normally we wouldn't even worry about that one, but that's about there. And then we choose x to be 4, we get y as 2, which is here. And then when we choose x to be 9, we get y as 3, which is here. So this graph is going upward, but it's not going upward very quickly. And in fact, it seems as it's kind of slowing down how fast it's going upward, almost. But that's what the graph looks like. And notice the dot on the left side, the solid dot, that's the very furthest to the left value, and that represents, of course, the x values that we can use are greater than or equal to 0. That's the domain. So we need to be able to sketch that pretty quickly, and really it's this point, this point, this point help us get that graph pretty quickly. So that's using these values right there, isn't it? We ought to be able to sketch that graph fairly rapidly. Well, I'm going to tell you roughly what it looks like. When we look at f of x is equal to the cube root of x, we'd go through the same process and would have something that looks similar to this. Let's say out here is maybe a -8, and here's a, let's say it's a -1 and a +1 and a +8. 1, 2, 3, 1, 2, 3. See, if we chose x to be -8, then y would be actually -2. So it'd be this point, would have this point, would have this point. And I'm sketching these in real quickly because, and if we choose x to be 8, then y would be the cube root of 8, which is 2. See, there's 1 here, 2 here, 3 here. So this graph is going to look something like this. Whoops. Almost looks like that cube root, except that we can use, that square root, except that we can use negative x values if we're dealing with a cube root, aren't we? We can take the cube root of a negative number, not of a positive number. So if we know what this graph looks like, those 3 reference points could help us draw a reasonably accurate graph. The next one I want you to be concerned about, the absolute value function, and just real roughly, that graph looks like a V, doesn't it? And you can fill in the details on how we would get that graph. Okay, I hope that you can reproduce that and you have that experience. On the next page, I want to look at the last 2 real quickly. So this reciprocal function or ratio function, and it's usually called reciprocal function. I think I said ratio before. f of x is equal to 1 over x. Now this presents, we can use positive x's and negative x's. We just can't use x to be 0. See, we can't choose an x value of 0. But we can certainly choose x values like 1 and 2 and 3 and 4. And of course, when we do, our y value would be, when x is 1, we'd have 1 over 1, which is 1. And then when x is 2, our y value would be 1 over 2, or 1/2. And when x is 3, our y value would be 1/3. When x is 4, our y value would be 1/4. If x were 10, our y value would be 1/10. You see that our y values are becoming smaller and smaller numbers that are closer and closer to 0. So if we were trying to sketch this, and I'm roughing this in quite a bit here, okay? So 1, 2, 3, 4, way out here someplace is 10. So when x is 1, y is 1. That's this point, isn't it? And when x is 2, y is 1/2. And when x is 3, y is 1/3. And when x is 4, y is 1/4. When x is 10, y is 1/10, just barely above that axis, isn't it? So we're going out, and this is where 1 is, we're going out and it's getting smaller and smaller, it's getting closer and closer to that x-axis, but it's always above it. Even if x is 100, y would be 1 over 100. That's a positive number, just barely above the x-axis. Now, something else that's going on here, though, we can certainly choose x values that are between 0 and 1, like a 1/2. And so in that case, y would be 1 divided by x, and since x is 1/2, 1 divided by 1/2, we would calculate as 2. And if we chose x to be 1/3, y would be 1 divided by 1/3, and 1 divided by 1/3 is 3. If we chose x to be 1/4, then y would be 4, actually. Okay, so if x is 1/2, y is 2. So we're talking about roughly here. There's what 1/2 is. If x is 1/3, we have a y value of 3. If x is 1/4, we have a y value of 4. Remember, this is 1, 2, 3, 4. We can't choose x to be 0. We can't choose that. So, but we can choose x's that are close to 0, and so we'd have this graph look like this. As our x's get smaller and smaller, closer to 0, our y values are getting bigger and bigger. What are we doing? We're making the denominator smaller, so the fraction, which is the y value, is bigger. And on the other hand, when we made our x's bigger, then that's making the denominator bigger. The fraction has a bigger denominator, and as the denominator gets bigger, the fraction gets smaller, so the y's are getting smaller. Now, what I left out is that there's no problem using x values that are negative. See, I could have chosen x to be -1 or -2 or -3. And in that case, I would get a y of -1, a y of -1/2, a y of -1/3, and so on. And I could have chosen x to be a -1/2. And if I did, my y would be -2, and so on. So without going through the details right now, I want you to recognize that here, if we chose negative x values, we would have the part of the graph that looked like that. Now again, we couldn't choose x to be 0, so in this case, let's notice the domain is the set of all x's such that x is not equal to 0. Or that would be from -infinity to 0, union with 0 to infinity. And the range here would be the set of all y's. Well, we have y's going up, up, up. We have y's going down, 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 but we have no y that's ever 0. So here we would have y is not 0. It can be any other number. And so that would also look like -infinity, except these are y values. So this is vertical. -infinity up to a y value of 0, union from a y value of 0 to positive infinity, but we're leaving out the y value of 0. Okay, the very last thing is a constant function. Okay? And a constant function would look something like f of x is equal to, let's just say, 3. Now, this is akin, remember if we were doing this without function notation, this would be like y is equal to 3, and I hope we would recognize that that's a horizontal line. Now, if we were trying to create a solutions table, whenever we choose an x, remember it says above f of x is 3. It doesn't have anything to do with x, does it? It says f of x has to be 3. Y always has to be 3. Okay, so when we choose an x value of 0, our y is going to be 3. If we choose an x value of negative 1, our y value's got to be 3. If we choose an x value of 2, our y value's got to be 3. If we choose an x value of 175, our y value is still 3. And so when we graph this, 1, 2, 3, here's where y is 3. No matter what x we choose down here, our y value is 3. No matter what x we choose here, our y value is 3. No matter what x we choose, our y value is 3. So all these are going to be up at a level of 3, and as we connect those, of course, that gives us the horizontal line. So this is the graph of f of x equal 3. Okay, as I said at the beginning of this, I want you to be able to anticipate what these graphs are going to look like without pulling out your calculator. And we're going to need to know what these graphs look like later on to have an idea of what more complicated graphs look like without using our calculator. So become familiar with these, please. Spend some time memorizing them if you don't have them memorized already, and how you can reproduce the graphs pretty quickly. Good luck on your homework.